All right, we are part 3 of section 4.1. We are going to continue talking about angle measurements and applications of those angle measurements. And before we get started, let's just do a little bit of discussion on linear velocity or linear speed versus angular velocity or angular speed. So what I kind of like to think about is you are on a track. Let's kind of think of this as like a circular track, and you're in lane 1 and someone else is in lane 6. And as you begin to run around the track, it is going to take the person that is in lane 6 a much faster speed in order to keep up with the person that's in lane 1. And this happens because if you're wanting to keep at the same distance while you both are at the same angle, it's going to take your speed and you're going to have to run faster in order to keep up with that person, right? So depending upon your radius, your speed is going to have to increase. So that speed is going to change based on your radius. When I think about angular velocity, the angle in which maybe like, I don't know, back in the day, you used to have these like kind of little things that would attach to your spoke of your wheel, right? And so let's kind of line those up there and we'll say that they're on the same line on this bike wheel. Well, as these turn, as these rotate around the bike wheel, okay, they're starting here and they're going here. As this angle changes, this speed is actually going to stay the same. So the speed of this little tab and this one is actually the same when we're pairing it with the angle. Let's hop back over to these notes. And this is a lot of information on this one particular picture. Ultimately, we're going to be looking down here at where we are comparing linear velocity in terms of angular velocity. I've put a couple different formulas here, linear speed and angular speed formula. You know linear speed. Linear speed is basically the distance over time. And angular speed is going to be your radian measurement over time. Now, if you do not know what this symbol here is, this is not a W. Looks kind of like a W, but it's actually the Greek letter, and that is called omega. So if you hear me mention that, you'll know what we're talking about. Okay, and that's going to represent your angular speed. But we're going to be talking about linear velocity in terms of angular velocity, or linear speed in terms of angular speed. And the main formula that you're going to need for that is this one right here, where we're talking about the radius times the angular speed. And another very important piece of information that you know is that one revolution around the circle is used to represent 2 pi radians. So when we're writing this, we need to be written in radians per time. If it gives it to you in revolutions, you're going to have to do some conversions. So let's go ahead and look at some examples. It says a wheel is rotating at 14 radians per second. So the wheel is rotating. That is our omega, or our angular speed. If the radius is 16 inches, what is the linear speed? So we're converting an angular speed into a linear speed. So we have v, which is our linear velocity or a linear speed, is going to be equal to the radius times the angular speed. They've given us the radius. And we know that the linear or the angular speed is 14 radians per second. And this is in inches. Okay, when I write my answer, I'm going to write it in terms of the measurement of length over time. Okay, so distance over time, whatever that is. So here I can multiply 16 times 14, and I will get 224 inches per second. So we can leave off that radians, and we can write it in terms of distance over time. All right, let's look at another one. A wheel rolls along the ground at 120 centimeters per second. Okay, so here again we have a wheel is rolling along the ground. Now, this is talking about the outside speed. It's rolling along the outside. So this is kind of like a car driving, right? Your car is driving on the road. That's its linear speed, or its linear velocity. So this is actually giving us the v. The radius is 5 centimeters. What is the angular speed? This is kind of having us work backwards. So this is saying, using that formula, giving us 120 centimeters per second. If I know the radius is 5 centimeters, what is its angular speed? So of course here I'm going to divide. And if I divide, then I will take 120 divided by 5. And those centimeters are going to cancel. And this is going to give me the angular speed. And this is going to equal 24 radians per second. So again, just working backwards and understanding what are the values that they are giving you and where does that go in the equation that I'm working with. Let's step it up a little bit here. On the next one it says, long before iPhones and Apple Music, individual songs were delivered on a 75 revolutions per minute, that's RPMs, revolutions per minute, and a 45 RPM circular records. A 45 RPM record has an angular speed of 45 revolutions per minute. 45 revolutions per minute. Now remember what I told you, that 2 pi radians equals 1 revolution. And when we write this equation, it must be in radians over time. So what I need to do is I need to do some converting here with this problem. So I need to take 45 revolutions per minute and I need to convert that into radians. So I need to say 45 revolutions times 2 pi radians. And that is going to give me 90 pi radians per revolution. Okay, let's keep going. Find the linear speed in inches per minute of a needle. So when you have a record player, it has a little needle that stretches out and that's what makes the sound go. The needle is 1.5 inches from the record center. So the radius is 1.5. So when I start these problems, I make sure I make a note of all of these important things that I have that it's asking me to do. Okay, so I now am looking for the linear speed, 1.5 inches, and I have an angular speed of 90 pi radians per minute. Okay, radians per minute. And I'm going to go ahead and multiply this out. I'm going to take 1.5 times 90 pi, and that's going to give me 424.1. Remember, we leave off the radians so we can have it distance over time, which will be inches over minutes. Okay, we have a couple others to do here. Let's do one more. This one's going to kind of be the same. A windmill is used to generate electricity. The blades are 10 feet in length. That's going to represent my radius. We've got a figure below here kind of help you. So these are going to spin around. It says the propeller is rotating at 4 revolutions per minute. So here you're kind of back to this problem again. So we know 4 revolutions per minute times 2 pi radians. So that will then go to 8 pi radians per minute. So we've done our conversions. We know our radius is 10. It says find the linear speed. So I can go ahead and just input that information in. 10 times 8 pi. And I have, I actually put minutes here, and that needed to be seconds. So that's correction I need to make there. Per seconds. And that's going to be, let's see, this one was feet. And that is radians per second. And so now I will have 80 pi, or I will have 251.3 feet per second. So once you get the idea of how to do your conversions from revolutions into radians, really inputting it into the formula isn't too hard. We're going to have one that's going to be a little bit more confusing, and this you're going to have to use some dimensional analysis. So if you've been in chemistry or science of some kind, you've done dimensional analysis before, and that's where this is going to come in. So it says a wheel is rotating 250 times every minute. Well, what's that mean? That means it rotates 250 revolutions per minute. Okay? Now remember, again, this is revolutions. We don't want revolutions. We want it in radians. So we need to do some conversions. 215 times 2 pi. Okay, I can go ahead and multiply that. That's going to give me 430 pi, and that will give me radians per minute. So I've got that conversion. They tell me the radius is 10 inches, and they want the linear velocity in miles per hour. So as you notice here, I don't have miles per hour. I have minutes and inches. So this is where your dimensional analysis will come in handy. We're going to start way over here. We have 430 pi radians per minute times 10 inches. If I went ahead and did that conversion, I would have 4,300 pi inches per minute. But I need that in miles per hour. So what we have to do is we have to go from inches per minute all the way into miles per hour. So I need minutes to first go to hours. So minutes, I know for every 1 minute, okay, so let's go backwards. So we can do it this way. We know that there is 60 minutes, right? 60 minutes for every 1 hour. So as long as I can cancel out that measurement and get it to what I want, I'm going to be in good shape. So I have hours in my denominator, and that's what I want. So this matches here, so I'm okay with that. Now I need to go from inches to miles, right? So I know that there are going to be 1 feet in 12 inches. So that's going to cancel out my inches and get it into feet. Now I know that there is 1 mile in every 5,280 feet. And look what happens. Inches will cancel. Minutes will cancel. Feet will cancel. And the only label that I will be left with is miles per hour. And so now I need to multiply all of my numbers here that I have. So I'm going to take 4,300 pi times 60, and I'm going to divide that by 1 times 12 times 5,280. And I'm going to use a calculator for that. And when I use my calculator, I'm going to get 12.8 miles per hour. So this is not only using the formula of linear speed versus angular speed, it is also using dimensional analysis.